Hello, I'm Vedant presenting our work, MViTac, Multimodal Visual-Tactile Representation Learning through Self-Supervised Contrastive Pre-Training. This is a joint work with Fotios Lygerakis and Elmar Rueckert from Chair of Cyber Physical Systems, Montan Universität Leoben, Austria. Humans assimilate knowledge through various sensory inputs, including vision, touch, sound, etc. This learning journey begins in infancy as seen in the video. Babies engage with their surroundings, gradually mastering complex interactions and seamlessly integrating multimodal representations, often without any explicit guidance. These early experiences lay the groundwork for skills utilized in advanced tasks, including stacking, grasping, and more sophisticated manipulation tasks, which we continue to develop in our later life. In one of the experiments, human subjects were given anesthesia in their fingertips for completely eliminating their tactile sensations. The resulting video highlights that when a single sensory modality is isolated, even elementary tasks such as lighting a matchstick become significantly more challenging, demonstrating the significance of learning joint representations from multimodal sensory inputs. In the realm of multimodal representations, it is evident that incorporating various modalities enhances outcomes. For example, in grasping prediction, the integration of tactile modality improves the accuracy of determining the success or failure of the grasp. Until recent years, most of the research has concentrated on supervised learning, especially in the case of learning multimodal representations for robotics. This approach involves processing multiple modalities through separate encoders, with the resulting representations often being concatenated for downstream tasks. However, this method does not fully explore the intermodal relationship between different modalities, neither the intra-modal relationship between its own modality. In context of data collection, particularly for supervised learning, the process of gathering labeled data is notably challenging. This is especially true in robotics, where a substantial amount of data is required for supervised learning to yield effective results. Consequently, this necessitates a shift towards self-supervised learning, which can potentially mitigate the challenges associated with the acquisition of large-scale labeled datasets. Unlabeled data can be simply acquired through random actions or simple collection processes involving humans or robots, as done in touch-and-go dataset. Self-supervised learning capitalizes on this extensive pool of unlabeled data to learn representations. Subsequently, the knowledge derived from these representations can be refined using labeled datasets, enhancing their applicability for specific tasks. These representations can be employed in downstream tasks, which may include complex manipulations, predicting the success of grasp, or classifying material properties. Recent developments in visual-tactile representation learning build upon a range of innovative methods. For example, the use of cosine similarity for aligning tactile and visual data has been applied in garment localization tasks. Another notable approach involves cross-modal conversion between tactile and visual images, though its application is limited due to challenges in generalizability. Guze et al. Notably stand out by utilizing tactile data and augmentations to learn self-supervised learning loss and learn downstream manipulation tasks, but it does not incorporate visual images. Historically speaking, earlier work in the field has employed supervised learning techniques. These methods typically involve integrating various sensory inputs, which are then concatenated and processed through a multi-layer perceptron to predict the success of grasping tasks. Our methodology capitalizes on the principle of contrastive learning, a predominant technique in self-supervised learning. In the framework of contrastive learning, the process involves an original image along with its augmented counterpart. Both images are processed through an encoder and a corresponding target encoder. The primary goal here is to maximize similarity between representations of the original image and that of its augmented version, thereby enhancing the efficacy of the learned model. Unlike scenarios involving a single modality, our study dwells into multimodality, dealing specifically with vision and tactile images. We work with the dataset comprising of n vision and tactile image pairs, where each of these is subjected to augmentation. These images are then processed through convolutional neural networks serving as encoder and their momentum-based counterparts. The architecture of these encoders is ResNet 18 backbone, pre-trained on ImageNet dataset. We also incorporate a 2-layer MLB projection head for each layer, which is designed to map the encoded representation into embedding space, which is crucial for contrastive estimation. The design also includes a momentum encoder, which along with the MLB projection head undergoes continuous updates throughout the learning process. Intra-modal learning aims at optimizing feature representations within the same sensory modality, such as visual to visual or tactile to tactile, as seen in green and pink respectively, to enhance the discriminative power of the extracted features and generalization capabilities of the model for downstream tasks. Inter-modal learning aims at aligning feature representation across the visual and tactile sensory modalities in order to develop a unified multimodal latent representation that captures the underlying relationship and shared attributes between these distinct data sources. In our model, we apply info and CE loss for each modality. This loss function is well regarded for its effectiveness and simplicity in implementation. As depicted, the info and CE losses utilize not only just LVV, but also for all the other loss functions. By the end of the process, we calculate 4 distinct losses. This includes LVV, visual to visual, LTD, tactile to tactile, and the other 2 intermodality loss. These losses are then weighted by intermodality coefficient, allowing for stability in the learning process. In our study, we benchmark our model against 3 distinct baseline approaches. The first was mentioned in Touch and Go paper, employing contrastive multi-view coding. The second was developed by Kerr et al. Is a self-supervised visual-tactile pre-training approach. The third involves traditional supervised learning, where all the available labels are utilized for training. The Touch and Go dataset is categorized into 3 main aspects: hardness, category, and texture. Hardness is the object's firmness or softness. Category classifies objects into various types such as raw materials, wood, steel, etc. Texture differentiates objects based on their surface feel, like rough or smooth. Our analysis illustrates that the graphs show that our approach, MViTac, excels in all the categories for visual, for touch, and visual and tactile modalities. In tactile modality alone, supervised learning slightly surpasses MViTac in hardness, but this margin is minimal. However, when combining visual and tactile data, MViTac significantly outperforms all the other methods. This clearly demonstrates the superiority of our method, particularly when integrating both intermodal and intra-modal learning along with the visual and tactile data, showcasing its enhanced learning capacity. In our study, we utilized Calendar dataset for grasp predictions involving 2 tactile images and a single visual image with the goal of predicting the success of grasp. We compared our method with contrastive multi-view coding and supervised learning approaches. Our method significantly surpasses CMC, a self-supervised method. However, it still lags behind supervised learning approach, an area for further investigation. In the future, we would like to integrate our work with reinforcement learning on real robots. Thank you for your attention.